Hello, in this video I'm going to take another step away from the Earth in terms of distance and talk about galaxies. So these are systems of stars and gas and dust and dark matter and other stuff bound together by gravity, essentially in their own little mini universes. And since the first one of these galaxies was identified, which is relatively recently, a little over 100 years ago, since then we have identified and predicted the existence of 200 billion to maybe even 2000 billion galaxies in the observable universe. So that is an enormous number of galaxies, and they range massively in size, structure, what they look like and such like. So there's quite a few bits that we need to unpick in all of this. So let's get some of the key terminology and descriptions down for galaxies. Let's start with this picture here. See, I've got a picture on the screen which is probably distracting you. So most people, when they think of galaxies that they would have seen pictures of, they'll think of the pretty ones. They'll think of these spiral galaxies. This is M31, Messier 31. This is the Andromeda galaxy, which is a close neighbor to the Milky Way, our galaxy. And I say this is M31, I mean it is. That's what captures your eye in this picture, this big spiral in the middle of the picture. But we've actually got two other Messier objects in this picture as well. We got this little blob here. This is a satellite galaxy of the Andromeda galaxy. This is M32. That is actually an elliptical galaxy. So we're already seeing here two main types. These are the two main types of galaxy: spiral galaxies and elliptical galaxies, which are more circular affairs, spherical affairs, I should say. And then we got another galaxy down the bottom here, which is Messier 110. So that's three Messier objects in one picture. So yeah, that's already pointing us towards a couple of main types here. We got spiral galaxies and we got elliptical galaxies, and I'll talk more about these in a moment. There's also irregular galaxies. So these are ones which have been messed around a bit, maybe in their structure, and just don't fit into the first two categories. So we need to unpick what's going on with these different types of galaxy. Also, in terms of size, then let's talk about sizes of galaxy. You can go from dwarf galaxies, which might just be a few thousand light years across. So you might get something which is, say, 3,000 light years in diameter. It'll have a few thousand stars. So we're counting in the thousands when it comes to stars. So you've got those dwarf galaxies. You've got supergiant galaxies at the other extreme. So in a supergiant galaxy, you might be looking at 300,000 light years across. So 100 times the diameter. And you're then looking in trillions or hundreds of trillions of stars. So massive range there in terms of the size and the number of stars in these galaxies. As a comparison for these, let's take our galaxy, the Milky Way, which we're looking at in terms of number of stars, maybe 100 billion stars, something like that. So we're fitting it in between these two extremes. But the Milky Way is a pretty substantial galaxy. It's bigger than average, but it's not crazily big. So that's what's happening there in terms of the size of individual galaxies. But then these galaxies, they get clustered together. You'll get clusters of galaxies, just like you get clusters of stars. You then get super clusters of galaxies. So there's I didn't mention the diameter of Milky Way as well, did I? So let's say 90,000 light years across. So again, puts it in between these two extremes. So you get groups of galaxies, and then these clusters of galaxies, then super clusters of galaxies. So the Andromeda galaxy here, M31, this is in what's known as the local group. So this is the cluster of galaxies that the Milky Way is a member of. And that doesn't mean to say they're particularly close. Andromeda is about 2.5 million light years away. So that's quite a distance getting to the other major galaxy in the local group. I mean, the local group is dominated by the Milky Way and the Andromeda Galaxy. They are the two big ones, and then there's a few other smaller galaxies dotted around, which might be satellites of these two larger galaxies. And then that local group is then part of a supercluster, which is, in our case, for the Milky Way and the local group, is in the Virgo supercluster. And this is something that you notice when you observe if you do deep sky observing, then there are loads and loads of galaxies in the constellation of Virgo. So they just happen to be in that direction. That's the direction where most of the action is happening in terms of our local cluster and supercluster of galaxies, is in the direction of the constellation of Virgo. So yeah, they group up into these clusters and superclusters, huge amount of variety. Before I get on to looking at these differences between the spiral, elliptical, irregular galaxies and looking at some of the pretty pictures, let's take a step back to the history of how people actually identified these things as galaxies. Because as you probably noticed if you've watched any of my previous videos, if you go back to the 18th century, all of these objects, these cloudy objects in the sky, were all referred to as nebulae, referring to their appearance as being cloudy. And that accounted for actual nebulae, as in the star formation regions, galaxies, globular clusters, planetary nebulae, supernova remnants like M1, the Crab Nebula. They all had that same description because people couldn't resolve any detail in their actual structure with the telescopes they had back then, or gather any other observational data that was useful. This then changed in the early part of the 20th century. So in 1912, there was conclusions drawn from a lot of Doppler observations. So looking at Doppler shifts of the spectra of these objects. I mean, first of all, the spectra of comparing a galaxy where you've got the combined effect of billions of stars to looking at, say, the spectrum of a nebula or a planetary nebula, and you'll see very different things, but that doesn't tell you in itself how far away these objects are. So we need some kind of evidence to show that these galaxies are much further away and they're actually external to our galaxy, unlike the nebulae and the planetary nebulae, which are internal to the galaxy. So this is where the Doppler shift evidence was coming in, because they were showing very different motion of these objects. So the galaxies were shown to have these relatively high Doppler shifts. So they're redshifted, they're moving away from Earth in the way that the other objects, the nebulae and the planetary nebulae, weren't moving away or aren't moving away from the Earth, because galaxies are external to our galaxy, whereas the nebulae and the planetary nebulae were internal to our galaxy. So the Doppler shift was giving that first bit of evidence that there was something going on here in terms of the location of these objects. Then people, a few years later, around 1917, there was evidence published to do with supernovae and other bright star events, where inside these galaxies, supernovae were so much fainter than they were in other locations when they were occurring. So this was giving a strong suggestion that these objects, which we now call galaxies, are much further away. So combining this sort of evidence and a few other bits, this all fed into the 1920s and the great debate when it was first decided, the conclusion was drawn that there were objects outside of our galaxy. The Milky Way up until the 1920s was considered to be the whole of the universe. From the 1920s onwards, people then started thinking, actually, no, Milky Way is just one galaxy amongst many inside a larger universe, and these objects are other galaxies. So from a historical point of view, this is how it was pieced together. Subsequently, of course, the quality of the equipment and telescopes and such like has improved massively. So we can see more structure in these objects now. We can see, just looking at these photos of things like spiral galaxies and their structure, and then nebulae and planetary nebulae, we can see these things are different. visually now by looking at these pictures. But of course, people weren't seeing anything like this picture through a telescope 150 years ago. This is, you know, high detail stuff, high resolution stuff. So yeah, this is relatively new that people have been piecing all of this together. Right, let's get back to these different types of galaxy then. Let's go through these three main types here: spiral, elliptical, and irregular. So we've already looked at this spiral galaxy here, the Andromeda galaxy. Here's another particularly famous spiral galaxy. This is the Whirlpool galaxy M51, one of the most easily recognized Messier objects. So yeah, M51, Whirlpool galaxy. Now you can really see here, because we're looking down on the plane of the galaxy of this spiral. You can see the structure where we've got this core in the middle, and then we've got these arms coming out. And it looks as though, when you first look at it, it always feels as though there should be a lot more arms. But you draw the core in, we've only got two arms coming out of the core. If you draw that arm going round there, and then we've got this arm going around here, I mean, that's making up the vast majority of the structure that we're looking at in this picture. This bit here, okay, you've got a sort of halfway between arm, which might be, but maybe that's just an extension of that one. So you don't get huge numbers of arms in these spiral structures. And this is what the spiral galaxies look like. But of course, we're just seeing the visible matter in here. And you get some galaxies where you see them side on, things like the Sombrero galaxy. Actually, I don't think I'll put a picture of the Sombrero galaxy in here, but you see that a bit more side on, where you see a bulge in the middle. So you've got this disk with a bulge in the center. Then you think, oh yeah, okay, well, this is how the matter in this galaxy is distributed. But not so. There's a lot more matter distributed in a spherical shape. This is just not all visible to us. Now, we've seen this when we spoke about globular clusters, about how a lot of globular clusters are distributed around this sphere rather than in the actual disk of the galaxy. Now, it looks as though, although people are still building, you know, various models about how galaxies actually form, but there's, I think the main theory is still that you're getting this star formation in these arms. You can see that the actual spiral arms are the bright bits. This is where the stars are. That you're getting these density waves. So as the matter is rotating around, you get waves of density, which then pushes the interstellar gas together and forming these nebulae, these star formation regions that then form stars. So you've got a density wave setup going on. And then that just creates certain areas inside the whole spherical distribution of matter where you're getting star formation. So it's concentrated in certain areas. At the center of most of these spiral galaxies, particularly the large ones, you're going to have a supermassive black hole right in the middle. So inside this central bulge, you've got a big black hole there. Now, we can't see that much of our galaxy. Okay, you can see the spiral arm we're in. You go out in the dark sky and you look overhead, you'll see the Milky Way stretching across the night sky. But the sun's a relatively long way out in terms of compared to the center of the Milky Way. You can't see much towards the center. If you start looking toward, into the disk, along the disk, through the arm, but there's so much stuff there, you can't really see that far. You can see further, if you see those distant globular clusters and things, if you're looking outside of the disk. So we can't see anything in terms of, visible light and such like from the central bulge of the galaxy and the supermassive black hole, any of the energy that might be getting released from matter that's going into or orbiting around that black hole in the middle. So, but yeah, that's the structure with this. And one thing, I was going to save this for the end, but I think I'll drop it in now while we're talking about distribution of matter inside these spiral galaxies. One thing that people noticed with this is when they were building their models of how galaxies behaved, and they started constructing these things called rotation curves. And this is where you are plotting the rotation speed against distance for matter. You take a line going from the center of the galaxy going outwards and say, right, well, how fast is all of this stuff moving as it rotates around the galaxy? And you plot out a curve of this. So we've got distance here, and we've got some rotation speed going on here. And when people plotted these out, they made their predictions, first of all. They say, okay, what is our model telling us based on what we can see, all this visible matter here and how it's distributed? Stick that into a model of how matter moves, and they came up with their prediction would be something like this. That's what they were expecting. Then did their observations of what was going on, and they found that it was something more like that, which is quite a long way out. Okay, you've got similarities up until this point, but then this is massively different in terms of the observation and the prediction. And the conclusion off of the back of all of this is that there is a lot more matter inside these spiral galaxies than is actually visible. This is what's referred to then as dark matter, because it's not visible, it's dark. And it's thought now in the models that people are building of these spiral galaxies that this dark matter is occupying some huge halo, this spherical halo around the galaxy. And that is affecting the motion of the visible matter. Of course, what this dark matter actually is very much open to debate. I'm going to do a separate video talking about dark matter itself. You know, it's hard to pin down what it is. It's dark, we can't see it. But there are a lot of theories about what it is. But it's now thought that in terms of actual mass in the universe, we're looking at around 80% of the mass of the universe is dark matter, and only 20% of it is visible matter. Of course, we've then got, on top of that, we've then got dark energy as well, which I'll also do another video on, which is saying, well, actually, the actual mass bit of the universe is less if we're going into mass energy, and what we were talking about in earlier videos, that relationship, you know, E equals mc squared, our relationship between mass and energy. Well, if you're saying mass and energy have got an equivalence, well, most of the mass energy in the universe is in dark energy. So we've got our visible matter, then we've got about 4 times that, or 5 times the visible matter going into dark matter. And then we're multiplying up again and saying, well, you add up all of your visible matter and your dark matter. Well, if you double that, that then gives you the dark energy. So we're only looking at a small fraction of the total mass energy inside the universe. So a lot has come off of the observations of spiral galaxies. Right, so I got a little bit sidetracked there, but I think that was a good place to drop it in. Right, let's look at a couple of other spiral galaxies then. So what have we got here? This is, what's this? This is the Pinwheel galaxy. So that will be M101. Although there's a few galaxies that get referred to as Pinwheel galaxies, but this is Messier 101. So that one looks quite nice. Again, you can see it's quite a similar sort of structure. Then we've got galaxies like this one. Right, so this is a barred spiral galaxy. So whereas on the previous ones, you can see we've got a nice round core here. The center of the galaxy is nice and round. Here on these barred spiral ones, we've now got a bar going across the middle. So the arms are starting that little bit further out. So rather than having a center with arms coming off, we've now got a center with a bar going through it and then arms coming off of that bar. So this one here is, I'd look this one up because it's not one I'm familiar with. This is M91 barred spirals. I don't think this has got an individual name. But this is then getting into how we go about classifying. And we've got another spiral one up here. You know, I mean, you can see galaxies all over the place on this picture. Look how many of them there are, all dotted over just this small picture here. I mean, you can just pick them out. I mean, that's 5 without even thinking, oh, there's another one. 6 of them, 7 of them. Just in this small picture, 8 of them. So, yeah, lots and lots of galaxies. So this is a barred spiral one. Here's another barred spiral. Again, you can see that central bar there. And this then leads into classification of galaxies. So for classification, we've got the Hubble system is the one that a lot of people use. So, you know, we've all heard of Hubble, Hubble's law, Hubble's constant and such like. I'll do a separate video on Hubble. I've already recorded it, so that'll be going up sometime soon, probably when I get into the cosmology bit. So we want to split up then spirals, which we'll denote with an S, and barred spirals, which we'll denote with an SB. So that kind of makes sense, doesn't it? Spiral, barred spiral. Then we're going to look at the arms and how tightly wound the arms are. So let's start with an S-type galaxy. So if we've got an S-type one, which has got fairly tightly wound arms, then we'll call that SA. If we've got slightly looser arms, then we can call that SB. And if we've got very loose arms, then we'll call that SC. We'll do a similar thing with Bs. So if we've got our barred spiral with tight arms, that will be an SBA. If we've got slightly looser arms, then we've got an SBB. And then you've guessed it, if we've got very loose arms, then we've got an SBC. So that gives us a way of classifying these galaxies quite simply. But we've still got other types of galaxy. We have got the aforementioned elliptical galaxies. So these are ones, I mean, you can see here, it looks like an ellipse. This isn't particularly pretty to look at compared to the spiral ones. But this one is a bit egg-shaped. This is M86. Pretty sure this is M86. Yeah, we've got another little galaxy up there as well. But yeah, let's go with M86. I think I've got that right. It's quite easy to get one elliptical mixed up with another one. But these are different. I mean, in spiral galaxies, you've got a lot of that visible matter of newly formed stars inside the spiral arms. These are young stars in the arms of spiral galaxies. Okay, you get older stars towards the core of spiral galaxies. In elliptical galaxies, these are old stars. They're a bit like just the core of the spiral galaxies, or they're, for the smaller elliptical galaxies, they're quite similar to globular clusters. And you've got these spherical or near spherical distributions of stars, which is more densely packed in the middle and reducing in density as you move outwards. But these are older stars. You haven't got star formation going on here. There's not much structure. There's not much interstellar matter. So you're not getting, as I say, this new star formation. And they range massively in size, elliptical galaxies. You can get tiny little ones, as I say, which are quite similar to globular clusters. You can get mega galaxies. I mean, this is a famous one, not just because it's elliptical, but because of this big jet coming out of it, which I'll get onto in a moment. This is M87. This is one of these supergiant galaxies, trillions and trillions of stars. It's just enormous, this thing. And you think, well, if this is one of the biggest galaxies around, and we're talking about hundreds of thousands of light years across, then what on earth is going on with this great big thing? I mean, look at the length of that jet that's coming out of it. And this jet here is thought to be an emission from the supermassive black hole and the matter that's accreting around it at the center of this galaxy. So when you get these supermassive black holes, so enormous, I mean, we're talking, you know, just epic amounts of mass has collapsed into and been has fallen into this black hole at the center of this galaxy. And you've got a lot of matter which is accreting around the black hole. And some of it will be falling in, some of it will just be orbiting around, you know, doing what it's doing. But you've got a lot of energy there. And you get matter will also be ejected. It's not that the black hole is just this, you know, big vacuum cleaner for matter and it just sucks all of the matter in. You've got a lot going on outside the black hole, and it will accelerate electrons and other particles up to relativistic speeds, really, really high energy, high speed particles, which can then get spat out. So again, we've got lots of magnetic fields and things like that going on because we've got all this ionized matter. And that's what's thought to be, you know, this big jet that's coming out here is these relativistic particles which are just being spat out and pushed away in this big jet away from the supermassive black hole. So that's what makes M87 particularly notable. The classification of elliptical galaxies is just how elliptical they are. So we're going for E on our Hubble system of classification, E for elliptical. We're going to go E0 will be something that's pretty much spherical. We'll go down to E7 for something which is fairly flat. You get an intermediate classification on this, you'll quite often see the Hubble sequence drawn out with your ellipticals going E0 to E7. And then you'll have your spirals and your barred spirals going that way. So you quite often see this. And then at the meeting point of all of this, you get these things that are called lenticular galaxies, which are a bit in betweeny. They're a bit between an elliptical and a spiral. So if you've got an elliptical galaxy which is flattened out enough, it's become more elliptical, more eccentric in its in how elliptical it is. It can start looking a bit like a disk. You get these lenticular ones which are a little bit sort of in between. They're a bit like a disk, they're a bit like a spiral, they're a bit like a elliptical. So it's almost like a spiral galaxy without having fully developed arms. So you get these lenticular ones in between. So that's the classification of elliptical galaxies. Then we've got, just to wrap up, I think this is going to be the last bit, irregular galaxies. Right, so you get some which don't have any particular structure. When we look at this one here, this is the Large Magellanic Cloud. So this is one of the satellite galaxies of the Milky Way. So you've got large and small Magellanic Clouds, and as you can see, this is just well, I mean, it doesn't have any structure at all, does it? It's fairly random structured, random shaped. You certainly can't say it's spiral. It doesn't have an elliptical shape. What you're going to call it? You're going to call it irregular. So these are just put down as IRR for their classification. So we've got the small Magellanic Cloud and the large clouds. These are not visible in the northern hemisphere, so they're quite southern in their location. And most galaxies are dwarf galaxies. Most galaxies around are smaller than things like the Milky Way. And if you've got small galaxies in a cluster of galaxies, they're quite likely to get disrupted by a larger neighbor, and they're going to get pulled around, and that's what's going on with this here. Of course, we don't see as many dwarf galaxies. There's loads of them around, but they're harder to spot because they're small. So most of the galaxies that we're going to look at when we're observing the night sky are going to be big spirals and big elliptical galaxies. They're the bright ones. Now, we saw a similar thing when we were looking at stars. Most of the stars that we see in the night sky are B stars, A stars. They're not the most common stars if you did a survey of every star in the galaxy, but they're bright. So we don't see as many of the G and the F stars, you know, those and the K stars, the cooler ones. We don't see as many of those in the night sky. There's loads of them about, but they're just fainter. So you get a bias in terms of the sample that we actually see in the night sky, just because the big ones are bright. So there you go. In terms of actually giving names, I mean, I've been talking, some of them have got actual names, these galaxies, you know, Andromeda Galaxy, Pinwheel Galaxy, Whirlpool Galaxy, etc. The others I've been giving the Messier classifications to, your M31s, etc. You also get the New General Catalogue. So New General Catalogue is one that you'll come across a lot. And that's where you'll see an NGC and then a number. You quite often know a 4-digit number or 3-digit number after it, things like that. So for Andromeda Galaxy, I think, I didn't check this before. I want to say 224, but again, could have that wrong. I don't know. But yeah, NGC 224. I'm so used to saying M31, but I think that's what it is. But you'll see those sort of identifiers just for knowing which galaxy is which. Because the Messier catalogue has only got 110 galaxies in it. I mean, 110 objects in it, I should say. Only about 40 of them are galaxies. So you've only got 40 galaxies thereabout that have actually got an Messier designation. So most of the ones are going to have New General Catalogue. So that's a pretty common way of talking about them. So there you go. That's an overview of galaxies, different types, bit on classification. And then, of course, the rotation curves, which is going to lead us into discussions of dark matter and dark energy. So, yeah, exciting times ahead.